Okay, hello everyone. I'm Aryan, and this is Combinatorics 2. I hope I'm audible. I hope I'm clearly audible and my screen is properly visible. Could you please confirm by writing yes in the chat? Great, thank you. So we're going to pick up where we left off last time in Combinatorics 1, and we discussed the elementary ideas from Combinatorics. So we're going to begin with permutations with repetition allowed. But before that, here's a warm-up problem uh, just to get ourselves started. And this is the problem, right? You have the word search, these letters SEARCH, and you have to form words from it, and you have to find the number of words you can form from the letters of this word, and they may or may not have meaning, and you have to use all the letters, right? In how many ways can I arrange these letters in these 6 blanks? You can write your answers in the chat, and I'm going to begin solving it in a few seconds. All right. So we have like S, E, A, R, C, and H, right? This is 1, 2, 3, 4, 5, and 6. 6 letters. And I have to arrange them linearly. So for the first blank, I have 6 choices. And for the next one, I have 5 choices. And then 4, and then 3, and then 2, and 1. Multiply all of them, we get 6 factorial, right? So the answer is 6 factorial. This is pretty clear. We did this last time as well, so I hope this part is clear, right? But now, what if not in this case our word was simple, so there was no repetition in the letters, right? We all the letters of the word search are unique, and that's why this was an easy problem, and the answer is just simply 6 factorial. But what if my word was something like this, like dribble, where the letter B is repeating, right? How would we solve such a problem? Uh, I'm just going to show you, and hopefully this is going to be clear, because what I'm going to do here is similar to what we did last time in when we tried to derive the formula for n choose r. But that's not what we're going to do. We're going to consider these letters again, right? And I have these letters written. And I have how many blanks? 1, 2, 3, 4, 5, 6, 7. So I'll make 7 blanks. Now the problem here is that these 2 letters are identical. So in any word that I make, I can interchange these 2 B's and the word will still remain the same, right? So let me try to solve the easier problem first. Let's say these 2 letters were different. Let me call this B prime, right? And in that case, what would the answer be if these 2 letters were not identical? I'm sorry, is there a problem with the voice? Okay, great, thank you. So what if these 2 letters were not identical? In that case, we have 7 blanks, and therefore the answer would have just been 7 factorial, right? Let me just check once again. 1, 2, 3, 4, 5, 6, 7. Yes, 7 factorial. So, but this is what happens when these 2 B's are not identical. And I'll just show you what we do in this case. But first I want to take up a simpler example. Suppose my letters were not these, but suppose my letters were just A, and B, right? And I had to arrange these in a line. Then one possible arrangement would be just A, B. And if these were distinct, then A prime, B, and there would be something like A prime, B, and then B, A prime. and B A prime B, and so on, right? So, and sorry, B A prime A, I meant, right? And if you look here, these two will actually count as the same in our case because these two A's are actually identical. We want to count these two things as the same, right? Exactly. So I'm going to do 7 factorial over 2 in this case, which happens to be equal to 2 factorial. But I hope you'll agree that if there were 3 A's, right, then there would be 3 factorial ways to arrange those A's, and for every 3 factorial arrangements, there would be for every 3 factorial arrangements of those A's, there would be one unique word that would be possible, right? And therefore, the answer here is 7 factorial over 2 factorial. I hope that's clear. So in this case, the answer would be 3 factorial over 2 factorial. Which is just, if you think about it, it's just 3, right? So, and if you were to think about it, there would just be like A prime A B and A B A prime, right? I meant A prime B A and A prime and A B A prime, right? So that's it, right? And this completes our discussion of repetition allowed. So what I'm saying is that if you have n objects in total, out of which A are identical of one kind and B are identical of yet another kind, and C are identical of another kind, then I can arrange them in. Then the number of ways in which I can arrange them is n factorial over A factorial times B factorial times C factorial, and so on, right? So I'm saying that I have n objects, and A are identical of one kind, B are identical of yet another kind, and C are again identical of another kind, and so on. And this has to be in such a way that A plus B plus C and so on is equal to n, right? I hope that's clear. You can feel free to ask any questions, or you can let me know if I'm going a little faster, right? Now here's a problem for everyone now, like, in how many ways can you arrange in how many ways can you arrange the letters of this word to form new words? Let's see. We have, let me just count the number of unique letters and write down how many times they appear in this word, so that I have a better idea of how to solve this, right? So I write D, and D appears only once, and then O appears 1, 2. So O appears twice. C appears only once. U only once. M just once. E again just once. N twice. Okay, you all got the answer. Yes, it's 13 factorial over 2 factorial, 2 factorial, 2 factorial, which is just 13 factorial over 2 factorial cubed, right? But just to be clear, like, let me just write it down anyway. There are 2 D's, and then there's 1 A, and we're done. And actually there's 1 I, and now we're done, right? Yeah. So this will give us like 13 factorial over 2 factorial cube, and that's the answer. Great. Now, I hope you realized why we divided this here, and this is going to be very useful in our next topic, which is something you'll find really interesting now, hopefully, and that is circular permutations, right? Now the question and we are trying to address here is, in how many ways can I arrange n people around the table? So imagine a circular table, maybe something like this. And I have like n blanks, n seats around it, right? So how can I arrange n people on these seats? One way to think about it is that let's just arrange them linearly, right? Suppose n is 5, right? Then I'll have A, B, C, D, and E, something like this. And let's just assume these other blanks are absent. Then in that case, I can rotate this table n times such that after one rotation B is at this position. Then after another rotation C is at this position, and that doesn't change what arrangement we're referring to, right? In all of these arrangements, if you go clockwise from A, then you'll find A, B, C, D, and E. That's why it's the same permutation. But now I'm going to leave it to you to reason out why. But if I were to arrange n people linearly, it would have been just n factorial, right? And I'm saying that I can rotate it in n ways because in one rotation I'll have A here. In another rotation I'll have B at the top. In another rotation I'll have C at this position, and so on, right? And that just gives me n. And we know by the recurrence that n factorial is just n times n minus 1 factorial. And if you just divide that by n, you just get n minus 1 factorial, which is fine. I'm perfectly okay with this approach. But maybe there's another way to think about it. If you remember last time we said, try to count the same thing in two different ways and maybe you'll get a beautiful result, right? Is there any other way in which we can reason why the answer is n minus 1 factorial and nothing else? What I'm going to say is, let's do one thing, right? Let's take this A, let's fix it here. And I'm going to say that if you do not want to put A here, and if you decide, no, I'm going to put A here, then what I'm going to do is I'm going to rotate this arrangement such that A comes here, right? So I'm saying without any loss of generality, let's consider A at this top position. And then if we arrange these linearly around A, then we'll get n minus 1 factorial, right? So if I had n things, I would just take one of them, any one of them, and I'd arbitrarily place them at any one position. And I'd arrange all the other ones, and I'd just get n minus 1 factorial because I'd have n minus 1 objects remaining because I took one away from n, right? I hope that part is clear. You can type in your questions in the chat as well. I'll be happy to respond to them, right? Now comes the interesting problem, which is an application of this. Yeah, sure, I'll explain it again. So what I'm saying is, you have to arrange n people around a table, right? So suppose these people are A, B, C, D, and E. Suppose we have just 5 people. And I just drew it a little badly. Assume these are equally spaced around the circle, right? So what I'm saying is that let's say there's so let's say I had to arrange these in a line. Then I would just arrange them in a line in n factorial ways. In this case, 5 factorial, right? Now what I'm saying is that if you arrange this in a circle, then if you had to arrange it in a line, it was 5 factorial. But you can rotate it 5 times. So in one such configuration, I can have A at the top. In another one, I can have B at the top. So what I'm saying is that the other one would look something like A here, and then B here, right? And C, D, E, and something like that, right? In another one, I can have C at the top. So just imagine rotating it again like this. And the arrangement remains the same, right? So I want to count the total number of distinct arrangements, and these two arrangements are considered the same. And if I were to rotate it again, having C here and then D here and then E here and then A here, it would have still been the same arrangement, right? And therefore I divide by 5 because there are 5 ways to rotate this, right? And therefore it's 5 factorial over 5, which is just 4 factorial. Yeah. So this is one way to solve the problem, but another way to solve it is that what I can say is that let's just fix A at the top position, and then we'll not consider any rotations. So in order to, you can think of it like, in order to undo the effect of rotation, we just fix one element here, so we can no longer rotate it, and the order won't remain the same in that case. So now if you put B here and C here, or if you put C here and B here, it'll make a difference. And there's no way that those can be part of the same permutation. And that is why this works. So what I'm saying is, let me fix A here. Sorry. Let me fix A here, and now I'm not allowed to rotate this anymore, right? So let's say we fix this, right? Now, if I were to assign the other spaces to other people, then those will be unique. I hope that's clear. Yes, exactly. And therefore the answer is 4 factorial. And all I did here is that I fixed one to undo the effect of rotation, right? Great. So I hope we can now come to this problem, which is just an application of the previous idea. And this is like a really interesting problem. When I first read it, I was also a little excited to solve it, also a little intimidated by it, but we're going to do it anyway. So this problem asks you to find the number of ways to color a cube with 6 different colors such that each face has a unique color, right? So what I'm saying is you have 6 different colors already given to you, right? And you have a cube. You have to find the total number of ways in which you can color that cube. And I hope you can notice here that rotations will affect our number of colorings just like they did in circular permutations, right? Now I'm going to ask you to I'm going to recommend that to be in a room where you have 4 walls and a floor and a ceiling. If you're in an open space somewhere, I'm going to recommend that you run, right? So that you can properly visualize it. So just run to a place where you have 4 walls and a floor and a ceiling. Just and once you're ready, we can begin with the discussion. So imagine you're in a room, right? And you have a floor, a ceiling, and 4 walls, right? I know it looks like like a parallelepiped, but just imagine this as a cube, right? So what can we do here? What did we do in the last problem? We just fixed one color we just fixed one person at one position, and then we arranged the rest. In this case, my concern is that if I color this bottom face green, and if I color this red, this right face, sorry, this left face red, and then if I were to rotate it such that this green face was somewhere here, and this face was somewhere here, if I were to read the diagram, something like I'm saying that suppose this face is red. These two will be part of the same permutation because I can rotate this along this axis and I'll just get this, right? So this is what we want to avoid. And for that, we're going to use the same approach of fixing one color and like arranging the rest. So I guess we can begin now. Enough hints. So if you're in a room now, look at the floor. The floor can be colored in if I were to assign any arbitrary color to the floor, and I'm going to fix that color, it doesn't matter, right? Because I can rotate the cube, and if you were to say that you're going to fix a color for a certain wall, I'm just going to rotate the cube, right? Such that uh, the the face with that color is the floor now, right? So for the floor, I'm going to fix the color, fix one arbitrary color. Remember that I have 6 colors, and now I fix any one arbitrary color for the floor. Right. And now if you look, I have 5 colors left. And now if I look at the ceiling, I have 5 choices for the ceiling. And now if I were to look at the other 4 walls, I have 4 colors left, and I can color them in 4 factorial different ways, right? So I'm saying 4 walls. And now this is just a circular permutation. And therefore you can color it actually not in 4 factorial, but in fact, actually no, sorry, it is actually 4 factorial, because we fixed the floor and the ceiling, and that's why it's that way. So the answer we ultimately get is 5 times 4 factorial, and let me try to explain it once again, just to be clear. So if you have 6 colors, let's say colors A, B, C, D, and E, then choose any one of them that you hate the most, let's say, and you give the floor that color. And it doesn't matter because I can just rotate it again, right? Now look at the ceiling. You have 5 ways to color the ceiling because you fixed one color, right? And yeah, there are 6 colors, so I'm giving an F as well. And I'm saying that, okay, let's just say we used one color here. So we have how many colors left? 4 colors. And we have 4 walls. And therefore 4 factorial. I hope that's clear. You can also rotate the 4 walls. That is 180. You can get the same color on the wall. I'm not sure I understand what you're saying. Although I think, yeah, I was doing it incorrectly. It's actually 4 factorial over 4. That's 5 times 3 factorial, I think now. Anyway, I'm just going to get back to this problem at the end. Maybe I'm doing it wrong. I'm going to think about it for a while, right? And for now, let's move on. And we're going to discuss something called complementary counting, which is something I didn't cover last time, and maybe I should have done it back then, because this was a problem that we kind of did last time. So what I'm saying is that we have to form phone numbers, if you remember that problem. Except that last time we did a problem of how many phone numbers exist, and we said that was if I had to make a 10-digit phone numbers, then the answer was 10 to the 10, right? But if digits didn't have to repeat, then we said the answer was 10 factorial. I hope you remember that, right? Because if I'm not allowed to do repeat digits, then I have 10 choices here, 9 choices here, 8 choices here, and so on. So that's 10 factorial. Now my question is, how many 10-digit phone numbers exist where at least one digit repeats? And here's the idea. Count the opposite of what we want and subtract it from the total number of things. So if you take all the phone numbers that are 10 digits, right? So you take all the phone numbers that are 10 digits and you subtract those numbers in which no digit repeats, then you get the number of phone numbers where at least one digit repeats. I hope you'll agree, right? At least one is just another way of saying that some digits repeat, right? And that would just be the opposite of the case where no digit repeats, and that's why it's 10 to the 10 minus 10 factorial, right? This is the basic idea behind complementary counting. It often helps us solve problems in an easier way when we do not want to count, let's say, for all cases. Like if you could have made cases where one digit repeats and two digits repeat and three digits repeat, and you'd get the same answer numerically. But here's an easier way to count them. Right? But what if we had to extend this idea? Here we did it for like one property, right? What if we had a number of properties? For example, we've all done this problem as kids, right? Okay. I'll just repeat that again. For if you have to count the total number of possible phone numbers of 10 digits, then I have 10 choices for the first blank, 10 for the second, 10 for the third, and so on. 10 choices, 10 blanks, and therefore my answer is 10 times 10 times 10, and so on 10 times, right? So that's 10 to the 10. And if I were to not repeat, then it's 10, 9, 8, 7. So like 10 factorial choices in total, right? Right. So what I was saying was we've all done these kind of problems at some point where you're like, you're given the number of people who read newspaper A and the number of people who read newspaper B and the number who read newspaper C, and then you're given the number that reads A and B and C and A and C, and then the number of people who read newspapers A, B, and C, all of the newspapers, right? And then you're asked to find the total number of people, right? That is fundamentally the same as what we're doing here, in the sense that uh, they're all related by this property from set theory. I hope you would have seen this somewhere. That is the cardinality of A union B union C is the cardinality of A plus the cardinality of B plus the cardinality of C minus the cardinality of A union B minus the cardinality of B union C minus the cardinality of A union C plus the cardinality of A, this is intersection. Plus the cardinality of A intersection B intersection C. This can be visualized as a Venn diagram as well. But first, let me do the easy case, right? Imagine you had a set of numbers. Let's say some set of numbers S, right? And I asked you how many numbers in the set are divisible by 6, and you know the number of numbers in the set which are divisible by 2, and you know the number of numbers which are divisible by 3. Let's say m numbers are divisible by 2. Divisible by 2. And n of these numbers are divisible by 3. then how many of these would be divisible by 6? I cannot really tell from here because I need to know the number which are divisible by both 2 and 3, right? And so let's just say that okay, maybe this was a bad example. So yeah, so for 2 and 3, the answer is just m plus n, right? So m plus n numbers will, wait, I think I'm confusing myself here. So m numbers are divisible by 2 and n numbers are divisible by 3. Then I need to find the total number of numbers which are divisible by, which are neither divisible by 2 nor divisible by 3. Then I'll take the number of the total number, right? I'll subtract the number which are divisible by a number divisible by 2. So let's just call it n of 2. That's just the number of integers in the set which are divisible by 2. And I'll subtract the number of elements in the set which are divisible by 3. And then I'll add the number of elements which are divisible by 6. Why is that? This is the number of elements which are divisible by neither 2 nor 3. It's because I first subtract the number which are divisible by 2 and I subtract the number of numbers which are divisible by 3. But when I do that, I counted the numbers which are divisible by 6 twice. And therefore I have to add them once again. Right? So this is actually the same as this property. So let's say these numbers are divisible by 2 and in the form of a Venn diagram, right? Divisible by 3. And I need to find the complement of these two. And I need to find basically these elements, right? So I'm saying you can find the total number of elements. You can subtract the number of elements which are in 2. Then you can subtract the number of elements which are in 3. But then you subtracted this region twice. So you're going to add it back once, right? And that's where you get this. If we were to generalize this, we get what's called the general principle of inclusion and exclusion. And it says, if we have a set that has n elements, and I know it can look a little intimidating, but it's pretty simple in some sense. So let's say I have a set with having n elements, and I wrote n like this for a reason, because I'm going to use this for some different notation. So if you see this weird looking n, like with this serif, it represents the total number of elements in A, right? In that case, if I have, in that case, let us consider n properties of these elements. Let's say alpha 1, alpha 2, alpha 3, alpha 4, and so on till alpha n are properties of elements in this set. Then I'm saying let n of alpha I be the number of elements with property alpha I, which means let n of alpha 1 be the number of elements having property alpha 1, right? N of alpha 1 for alpha 1, and then n of alpha 2 elements have property alpha 2, right? Then I want to find the number of elements having none of these properties. And I'm going to do the same thing here. First, I'm going to take the total number of elements, and I'm going to subtract the number of elements which have alpha 1. I'm going to subtract the number of elements which have alpha 2, and then I'm going to subtract the number of elements which have alpha 3, and so on for all of these properties. Then I'll take these properties 2 at a time, and I'll add them as we did last time. So if I were to imagine this as again as a Venn diagram for 3 elements, for 3 sets rather, then I need to find this area. And what I'm saying is that I first compute the size of this whole thing, and then I subtract this region, then I subtract this region, and then this region. But then I'll have to add back these intersections, and then I'll have to subtract this middle region once again because I counted it one extra time, right? And that way we get this answer. I hope this is clear. Could you please just confirm if this is clear by writing yes in the chat, or you can ask any questions if you want. Great, thank you. Okay, so now one of the last things I had for this session is computing n-chooser and recurrences, and we'll solve a few problems as well. So if I had to compute n-chooser, as we discussed last time, yes, it does. It does follow addition and subtraction alternatively. So you first subtract, and then you add, and then you subtract, and then you add, right? So these are taken one at a time. So for taken one at a time, you subtract, and then taken two at a time, you add, and then taken three at a time, you subtract, and so on, right? I basically just generalized this idea for this set, right? Okay, so now let's talk about recurrences, and this is something that you would have done maybe in under dynamic programming as well, but I'm just going to quickly cover it up just to be sure we all understand it, right? And we're going to take it from the perspective of combinatorics. The idea is that let me just take one problem for an example, and that is find the total number of, wait, let me just type it out instead. Right. So I have to find the total number of binary strings of length n where no two zeros are adjacent. It often happens that it often helps in combinatorics that when you do not understand how to solve a problem, giving it a name can be helpful. So let me just call this problem. Let me just call the answer to this problem an. So an is the total number of binary strings of length n where no two zeros are adjacent, right? So I consider n blanks, just like we've been doing ever since the beginning of combinatorics, right? And in this problem, I want you to consider just the first blank. I can either have a 0 here or a 1 here, and those two events will be mutually exclusive, right? If I put a 0 here, there's definitely not a 1 in this blank. And if I put a 1 here, there's definitely not a 0 in this blank, right? And therefore, these two events are mutually exclusive. So if I solve the problem for 0, if I put 0 here, and if I solve the problem for 1, then I can just add the solution to both of these problems, and that will be the value of an, right? So if I had 1 here, the problem just reduces to the number of binary strings of length n minus 1. I hope you'll agree. These are n minus 1 blanks because this in all is n blanks, right? And and so for case 1, where the string must begin with 1, so it begins with 1. In that case, my answer will be a of n minus 1. And if I were to consider the case where I put a 0 here, then we have the condition that no two zeros are together or adjacent, right? That means I cannot put a 0 here. I hope you'll agree. Which means I'll have to put a 1 here, and I do not have a choice. which reduces this problem to filling n-1 blanks such that with zeros and ones such that no two zeros are together. So case 2. Begins with 0. And the answer is A of, so this is n-2 now. And we get this recurrence. And if you were to look here, this looks very similar to the Fibonacci sequence, right? The recurrence of the Fibonacci sequence. And yes, this is the Fibonacci sequence. So if I had, now I'm just left with a base case. And if I had to fill one blank, then I would just say A of 1. And there are just two ways to fill that one blank. And so the answer is 2. And I just solve A of 2 as well. And that would give me the two base cases. And then you can just compute this with a recursive function. And you can tabulate it. And you can make it bottom up with dynamic programming. Okay, I should re-explain case 2. All right. So what I'm saying is, the problem says that I'm not allowed to use two zeros which are adjacent. So if I were to begin my string with a 0, let's say I put a 0 here, then how many choices do I have here? Can I put a 0 here? I cannot, right? Because I cannot put two zeros which are adjacent. Therefore, the only choice I have for this blank is a 1. And that reduces the problem of filling n blanks to n-2 blanks, right? Which is nothing but A of n-2, right? And if I were to if I for the other case, just to re-explain, for the other case, if there were a 1 here, then I can put a 0 here or I can put a 1 here. I mean, this problem is, this still remains the problem of filling n-1 blanks. And that's why we get this, right? And so A of 2 will be what? Let's just try to do it manually. 1, 0, 0, 1, and 0, 0. I don't think any other is possible because 1, 1 is not allowed. So that's it, right? And so this is 3. And you see the sequence will become, if you try to evaluate A1, A2, A3, and so on, and you get the sequence, you get 2, 3, 5, which is just the Fibonacci numbers, right? So my idea here was that if we do not know how to solve a problem, give it a name and maybe try to think in terms of one end of what we're doing, right? Maybe try to fill one blank and see how you can solve the rest of the problem. Maybe try to express it in terms of the original problem, and that often gives us the answer. In fact, I can look at the recurrence for n factorial in another way, right? You remember n factorial was nothing but the number of ways to arrange n things in a line, right? So I had, let's say like things A1, A2, A3, and so on to AN, right? Then I'd have, then I can just fill this blank in n ways. And the problem reduces to filling these n-1 remaining blanks. So I'm saying, let me call the number of ways to arrange n things in a line as let's say an, lowercase a, because I've already, you know. So let me call the problem of filling n things in a line as an, and then I can fill the first blank in n ways, and the problem reduces to filling n minus 1 blanks in and the problem reduces to filling n minus 1 blanks with n minus 1 objects, which is just arranging n minus 1 objects in a line, and that will just be a of n minus 1, right? And we get this. Which was nothing but the recurrence of factorial, because n factorial equals n times n minus 1 factorial. So suppose you didn't know how to arrange n things in a line, you could just give it a name, let's say an, and you could say that, okay, there are n ways to arrange the first thing, and the rest of the problem reduces to filling the rest of the blanks, the remaining n minus 1 blanks, and that's just an minus 1, right? And therefore we get this as our answer. Another thing we discussed today was permutations with repetitions, and it can be applied to the problem of grid paths. So if I had a square grid, let's say an n by n grid, for now let's just say it's just 4, and you start here and you want to reach here, and you can only go left or up. You're only allowed to go left or up, and you have to make sequences of you want to find how many such paths exist from here to here, such that you can only move either left or up. So you can either move like this. This is a valid path, and this is a valid path, or this is a valid path, right? What now? How do we solve this? The thing to note here is that whatever path I make, it has to go right 4 times, and it has to go up 4 times, no matter what path I make, right? So if I did this, maybe something like this, I have to go up once, twice, thrice, and 4 times, right? And then I have to go right 1, 2, 3, and 4 times. And no matter what path I take, I'll have to go up 4 times and right 4 times. And then the number of ways in which I can go from this source to this destination will just be the number of ways in which I can arrange these instructions of going up and left, right? Sorry, up and right, in fact. And we know how to solve this. This is how many objects? 1, 2, 3, 4, 5, 6, 7, 8. And you have 8 factorial over 4 factorial, 4 factorial. And that will be the number of paths from this vertex to this vertex, right? But there's another way to do it, and that is by dynamic programming, which is to say that if I had to go from here to here, let's say, right, then I can approach this vertex from either from the bottom or from the left. Let me do it with a thicker thing, right? Let me go it from I can approach this from the bottom, or I can approach this from the left. And the number of ways in which I can approach this is the number of ways in which I can approach it from the bottom plus the number of ways in which I can approach it from the left, because these are disjoint events, right? And what you can see is that let's say this is vertex 4, 4, and I want to reach vertex n comma n. So let me call that f of n comma n, the number of ways in which I can reach from 0 comma 0. I'll call this 0 comma 0, right? To vertex n comma n will just be f of n comma n is equal to f of n minus 1 n plus f of n and n minus 1, right? And then I can just form my base cases and solve the problem, right? Exactly. Great. So what do we have next? Yeah, that's pretty much it for today. If you have any questions, feel free to ask them. If you want me to explain anything again, I'd be happy to do that, right? The factorial way. Okay, you're asking about this recurrence, right? Uh, okay, you mean for grid paths? Okay, yes. For grid paths, what I'm saying is that any path that takes me from 0 comma 0 to 4 comma 4 will require me to move right 4 times, and it will require me to move up 4 times. So if you notice that this distance has to be covered, so I have to move right 4 times, and I will have to move up 4 times, right? So I'm saying let's let's take 4 R's and 4 L's, and any arrangement of these, every unique arrangement of these will give me a unique path from the source to the vertex, to the destination, that is. Uh, so in how many ways can I arrange this? That's just 8 factorial over 4 factorial 4 factorial, and that's why we get that answer, right? Great. Do we have any questions? Any more questions? Okay, great. So I had thought of discussing the combinatorial proof of the binomial theorem if time allowed it. So I think we have a few minutes, so I can take that up. I Let me just introduce you to the binomial theorem, and that says x plus. Sorry, if I had to expand something like this, the expansion looks something like n choose 0, x to the 0, y to the n, plus n choose 1, x, y to the n minus 1, plus n choose 2, x square, y to the n minus 2, and so on till n choose n, x to the n, y to the 0, right? Now this thing is, it looks pretty intimidating at first, and when I first tried to prove it, it so happened that I used induction. But this can be, this complicated looking theorem can easily be proved using combinatorics. And here's the idea. I consider x plus y written down n times, and that's what multiplication is, right? I'm just multiplying x plus y by itself n times, and I'm just writing it down like this. like x plus y one last time. So just when I say this, I mean this x plus y is written n times, right? So how do I multiply such a big expression? I take one term from each bracket and I multiply it, right? So if I had to find the coefficient of x to the n, and there are like n brackets in here, right? So I'll just take one term from each thing, and that would give me a unique term in its expansion, right? But once that's done, how do I find the coefficient of x to the n? The idea is that it's basically just I'll have to multiply this x with this x, and I choose this x term from every bracket, right? The term containing x, and so there's no coefficient, right? So x times x times x times x and so on. That'll just be x to the n. But now, what if I have to make x times y to the n minus 1? Then I take x from any one of these brackets and y from the rest of them, right? So I choose any one of these brackets and I say that from that bracket I'm going to take the term with y. That is this y. I'm going to multiply it by x from all the other ones, and that would give me n choose 1 times n choose n minus 1, but like sorry times sorry that would just be like n choose 1 because like I'm going to take y from this bracket, and that's why this is n choose 1, and then you can realize what I'm saying, right? So if I wanted the x square term, like the term containing x square, then I would okay, apparently I'm writing this down all wrong. So I have x plus y. And yeah, this is written n times. So what I'm saying is that to get x to the n, I'll just multiply this term with this term and this term and so on. I'll take the term containing x for all the brackets, right? And that'll just give me x to the n, and the coefficient will be 1. And then if I have to make uh, x y to the n minus 1, then I need x y to the n minus 1. Then from one of these brackets, I'm going to take a term containing x. And from the others, I'm going to take the term containing, I'm going to take the term containing y. In fact, this is why I was confusing it. Let me write it in order. X to the n minus 1 times y. Then I'm just going to take y from the other, so x from the other brackets and y from this one. And that's because it's just y to the 1. And I can do this for any one of them, right? So I can either choose the y term from this bracket or from this one or from this one. And that's why I have n choose 1. And if I had to make y squared, then I would choose y from 2 of these, right? And the term containing x from the rest of them. And that would give me n choose 2. X to the n minus 2 y squared, and so on, right? I hope you get the basic idea. I guess we can end the session then. Thank you so much for attending, everyone. It was great to have you. I know I made a few mistakes here and there, but yeah, I think we can end it here. Thank you, everyone. Great having you.